Hello and welcome to Toddcast number 53. Picking up where we left off from the last one, and that is going to start looking at more complex redox reactions. We last time looked at what happens when you use lithium aluminum hydride or sodium borohydride and how they can reduce carbonyls to alcohols. And carbonyls we looked at included aldehydes, ketones, and esters. I'm going to stay along that same path. Big thing to remember is that sodium borohydride, because B is less electronegative, is less reactive. It only reacts with aldehydes and ketones. Lithium aluminum hydride reacts with any carbonyl we throw at it. So let's go ahead and just see where we left off. So this is a ketone. And for reduction, I could use sodium borohydride or lithium aluminum hydride. A general rule in chemistry is you kind of want to use the least reactive reagent possible. You don't want to ever overdo it and possibly get side reactions. So generally you want to aim low, barely get it done. But because this is chemistry on paper, I don't really care as much. So I'm going to throw either reagent at the different compounds and figure out what happens. So with a ketone, ketones have 2 bonds to O. If I had a reducing agent such as lithium aluminum hydride, reducing agent because it's rich in H, it's going to reduce it. You're going to end up getting the same 4-carbon chain, but instead of having 2 bonds O, you're going to end up with 1 bond O. So you're going to end up adding an H and an H. So you'll notice that I have now introduced the fact that you get stereochemistry involved. So just like we had with an alkene, we have an sp2 hybridized carbon with a carbonyl. So you're going to attack in front or in back, which means you can get either the S chirality or the R chirality. And you should get a 50-50 mixture of the two. So just like we did with all previous reactions, we need to consider retroselectivity and stereoselectivity. In this case, the retroselectivity isn't all that significant. We are only going to react at the carbonyl carbon. We add the H minus. So we know where it's going to react, and it's not really a choice of any other carbonyl on this compound. But I do have to worry about coming in front or back, so stereochemistry. So next on the agenda, we have an aldehyde. Sodium borohydride only reacts with aldehydes and ketones, and conveniently that's what this is. And so in this case, we have NABH4. That H minus can attack this carbonyl. This 2 bonds O is going to kick up and become 1 bond O. We saw the mechanism earlier. So we're going to end up with the original H and the reduced H. Not worrying about the chiral center because we have 2 H's. So this wasn't chiral, I don't assume. This is sp2, so it's not chiral. In the end, 2 H's, so no chirality to concern ourselves with. Sodium borohydride, again, only reacts with aldehydes and ketones. This is a ketone. This is an aldehyde. So as long as I have 2 equivalents or 2 equivalents worth of H's, then I should be able to reduce them both. Probably going to attack this one first because it's more available through steric hindrance. But as far as preference of which one it reacts with, I'm going to say this one might be mildly more reactive, just aldehydes over ketones, not only because of steric hindrance, because R groups donate and help stabilize the plus. This one, H doesn't donate as much. So slightly bigger delta plus and less sterically hindered. So it's going to react with that one, followed by the other. It doesn't really matter in this case, as long as you note that it's going to reduce both. So reduces the aldehyde and the ketone. The aldehyde gets reduced to a primary alcohol and no chiral center to worry about. The ketone gets reduced, and I do need to worry about this center I form here because I have an OH and H, the side of the ring without the substituent and the side of the ring with a substituent. So note that you should get 50-50 of these two RNS if this was the only chiral center. So here's where the tricky part comes in. You didn't give the information, but there is a second chiral center. So because of that, I don't know for sure. But what I do know is that if it was in front, then the OH would go predominantly in front because the H would come in from behind. And if this was in back, H would go in front because forcing the OH in back because it goes to the side of less steric hindrance. So we didn't put the chemistry stereochem into this, but we do not get 50-50. That said, if this is a 50-50 mixture to begin with, then we will get racemic mixture, no chiral activity. So if it's optically inactive to begin with, it'll be inactive in the end. And last but not least, we have a carboxylic acid. So it is not a ketone or an aldehyde. So therefore, we can only use lithium aluminum hydride. So it's going to reduce not one, but two CO bonds. And so we add two H's to replace the two bonds to O. No chirality here. Whatever chirality we had here doesn't exist because they're equal. So it's an achiral process. Don't have to worry about stereochemistry. So the only ones we had to worry about it was the ketone turning into the secondary alcohol in either R form or S form, and then the two carbonyl species. But again, because I did not specify a chiral center in the beginning, it kind of took away any need necessitated in this one. If you are given a chiral center, pay attention to chirality. If you're not, like in that case, I didn't give it to you originally, not pertinent. Okay, onward we march with more of these reactions. We mentioned MCPBA earlier and just shorthanded it to being some R group connected to a carboxylic acid that's actually known as peroxy acid and has an extra O in it. It actually, or back when we looked at it before, it inserted into a carbon-carbon double bond. So let me just revisit that real quick. The reaction you know that this does when I use it, that same reagent, RCO3H, most commonly you're familiar with MCPBA, it inserted an O into that carbon-carbon bond. So it ends up, and we'll look at the mechanism in very minimal detail, but it ends up doing the same thing. It inserts an O into there, which is an ugly, unstable bond that very, very quickly will rearrange to where this will go there, this bond will go to that spot, and this bond will go there, which will leave me with, let's leave the atoms in the exact same place, which you know I like to do. So my red O, which was right around there. I now have this red bond to there. This red bond is now there, and this black bond that I had before is there. Meaning I end up with a carbon with a double bond. Sorry about this. Carbon with a double bond to O here, and an OR group here. So I'm going to erase what I wrote and let it come in as a product. So it's an oxidizing agent. You end up getting an ester known as a Baeyer-Villiger reaction. We're going to focus on this when we get to the carbonyls. But for now, I just want to note these oxidizing agents that we use for alkenes, some of them are going to come back to visit us again with other compounds. So a ketone will be turned into an ester. Rich in O, so it causes oxidation, goes from 2 bonds O to 3 bonds O. Also mentioned that a cysteine residue combined with a cysteine residue to form what's known as a disulfide linkage. This is a poor representation of a protein that has a cysteine residue on one spot, and then further down the chain has another cysteine residue that have formed a disulfide linkage. You can form it from cysteines in an oxidation process. That means you can also get rid of it in a reductive process. So something known as beta-mercaptoethanol. And I will leave this to the biochemist to teach you. But this H can be used, this H right here can be used as a reducing agent. So it can add H's. So in doing so, it undergoes disulfide reduction, turns the 2 sulfurs of the disulfide linkage back into 2 cysteine residues. So this would be a cysteine, and this would be a cysteine, and the rest would be whatever the protein is. Some amino acid here, here, so you have a whole bunch of amino acids before you get to the other cysteine residue. Okay. Had also alluded to zinc and HCl earlier. And again, I'm introducing these in a kind of a scatter plot fashion just to show you what happens when we use carbonyls, what they turn into. This is getting kind of ahead of ourselves because this is going to be more in chapter 19, the carbonyl chapter. But because carbonyls can be reduced to form alcohols, one also mentioned they can be reduced to form other things. So apparently carbonyl or ketone specifically can be turned into an ester. Ketones can also be reduced. We saw how we can reduce them to an alcohol, get rid of one of the pi bonds to O. It ends up we can get rid of both bonds to O. So instead of just the pi bond, get rid of them both. So when I have something rich in H and a metal, just like before, I can add a couple of H's. Wolff-Kishner reaction, I'm going to go into the mechanism when the time is right. But for now, it can give away a couple H's from there and there. Two of the H's will go on here. The other two H's will become part of water, and then you'll end up with an N2. I don't care as much about the mechanism, and I probably shouldn't even emphasize that we're going to do it in this chapter. I just want to emphasize the overall picture of oxidation and reduction. So rich in O, oxidizing agent. Rich in H, reducing agent. Rich in H, reducing agent. Okay, that's the main point of that. So want to toss one last example. This is going to be somewhat important, progressively more and more important as we go, but somewhat important in this chapter. And that is not only can I make a single alcohol, but I can make a diol. And there's a couple of different diols. We mentioned a geminal diol where both OHs are on the same carbon. You can also make OHs where they're on different carbons. And so this is where you have to combine what you learned in your travels in alkene chemistry. Hang on to that. You're adding in more reactions. And so synthesis, again, is going to start with some compound. Most roads will pass through alkenes in this, at least in this semester. And then moving oxygens from one carbon to another, increasing bonds O, decreasing bonds O, that's going to be kind of the extra piece we add into it. So you're going to have to start seeing that just one extra step added on to what you've already sort of programmed your head into recognizing. So let's do our inventory as always. Number of carbons, 5 in the ring, plus a 6 and a 7. So 7 carbons. 1, 2, 3, 4, 5, 6, 7. Okay. Let's go ahead and number it. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. The O is on 2. The O is on 6. So somehow these had to turn into O's. The reaction you hopefully remember for an alkene, where you break a ring open, ozonolysis. So if I treat this with O3, I'm going to use dimethyl sulfide as my solvent, my workup reagent. So if I do that, I will end up with 1, 2, 3, 4, 5, 6, 7 with 2 carbonyls. So here's where the new piece kicks in. How do you convert ketones into alcohols? And that's where reducing agent kicks in. I'm free to use any of the 2 I know, sodium borohydride or lithium aluminum hydride, but because I do not want to overdo any reaction, I'm going to use the weakest possible reagent I can and still get away with it. Ketones and aldehydes react with NABH4. I'm going to have NABH4 as my first reagent in. And I want to do this in some sort of ether. So I'll say like ET2O, like diethyl ether, THF, something like that, followed by some sort of protic quenching. Water with weak acid, methanol with weak acid, heck, just methanol by itself will quench it and stop it at the alcohol. So for this one, I did ozonolysis to generate the ketone and break the chain or the ring open and form a chain. And then I reduce those ketones into a secondary alcohol using NABH4. Okay, I'm going to get rid of what I've written because one more reaction is going to kick in. So hopefully this one makes sense. Next on the agenda, I want to turn a carbonyl into, again, a straight chain. So let's number our carbons. I'm going to start with the product 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this is going to be kind of weird. I believe I've broken open a ring, which means ozonolysis has to be involved somehow. But ozonolysis cleaves an alkene. So I'm going to have to turn this ketone into an alkene somehow. So I'm going to start doing some sort of reasonable guess at what I'm going to have. I need to get an alkene, which means I need elimination. You don't eliminate a double bond to O, you eliminate a single bond to O. So I'm going to have to somehow form that and eventually turn it into this. Luckily, because every single carbon is equally substituted, as in there are no other carbons coming off any point of the ring, I can get away with E1 or E2. So I'm going to go with E1 just because rearrangement, if it does, isn't going to mean anything. And then it's now down to exactly what we did up here. Exact same thing we just had, and that will be to cleave here, which will give us carbon 1 as an aldehyde connected to 2, 3, 4, and 5, which will also now be an aldehyde. 2, 3, 4. And just like we did before, last step is going to be reducing the aldehydes now. So I have an aldehyde. And an aldehyde. I'm going to reduce them both to primary alcohols. So I already know these steps from before. NABH4, step 1, step 2, protic workup. And then I know this one was O3. I'm not going to put the 1 because we do it in the DMS. So that one I'm set with. From here to here, I'm going to go with just concentrated H2SO4 and heat. And then I have another reduction. So sodium borohydride is going to get its work out today. NABH4 first, followed by protic work. I could use lithium hydride for either of these steps, that's fine. I could convert this into a BR with PBr3 and do E2 elimination with a strong base. It really doesn't matter that much. You want to do as few steps as possible. In actual chemistry lab synthesis, if you're actually in the lab, you want to use the cheapest reagents that get you the highest yield. So whereas on paper, we always say do it in as few steps as possible, just because it's less writing, easier to process. The best synthesis pathway is usually the fewest steps, but every now and then an extra step that ends up doing a better reaction, a two-step reaction might be cleaner, cheaper than one step, then sometimes you'll do that. But for this one, fewest step possible, reduce the alcohol, eliminate by E1 to the double bond, ozonolysis to break the ring open, NABH4. So if there's any take-home message I have here, it is that I want to, if possible, just learn as many of these steps as I can and go through the various reactions that I know to get to an alkene. Now, I looked up here and thought, oh my gosh, they gave me a different pathway. So let's consider what the heck that pathway was. So this pathway is good based on everything I've been learning, but here's the crazy thing that you're going to run into. So I just mentioned as few steps as possible is ideal. I did 1, 2, 3, 4. Now when I'm looking at this, it's saying, nope, there's a better way to do it. So we just learned, and although I'm not going to necessarily bring this up until chapter 19 as far as test goes, we could do bare villager, which means use a peroxy acid. If we do that, we turned it into this ester. And an ester, in this case again, it's still 1, 2, 3, 4, 5 carbons. Esters can get reduced, but you have to use lithium hydride. So if I use lithium hydride, that's when you need a stronger reagent working it up. So mild acid. If I do that, I will reduce this carbon through 3 bonds O to just 1, and I will cleave that carbon-oxygen bond. So ozonolysis is the only reaction we have to cleave a carbon-carbon bond, but we also have one to break carbon-oxygen bond. And so I was programmed, because I'd just done this ozonolysis one, to try to go through ozonolysis and take 4 steps. But apparently there's a better way. This is going to be one of the things that will be, I don't want to say bothersome, but definitely will start creating some sort of concern. And that is, how many different ways can you synthesize the product from the reactant? And we're going to learn very quickly, with this larger pool of information you have, larger number of reactions, you can find multiple ways to go from a starting material to a product. The best way, at least for tests on paper, can be the fewest steps. So my 4-step process, which I was so proud of because I avoided a 5-step process, and so it was 2 steps too many. Best answer was going through 2 steps. Bare villager to turn a cyclic ketone into what's known as a lactone. A lactone is a cyclic ester, and then reducing the ester using the stronger reagent lithium hydride to get to the 5-carbon diol. So at this point, I'm hopeful that you trust the reactions, know the reactions, but there's no doubt going to be a little more panic about all the different ways we can do synthesis. So wanted to introduce this early on, and that is, there is more than one way to go through most of these synthetic routes that we're going to be doing. I'm sure you're sitting there and you can't really ask us this is one-way communication, but I'm assuming you're saying, what if I did this lower one on the test? You can end up with partial credit, but you lose a couple points for not doing the shortest, most convenient route. So if it says the fewest steps possible, you do this. If it said going through some process where you had to get a cyclic alkene, then it'd be this one. So the question will specify, but typically it's fewest steps as possible. This would be full credit. This might be, I don't know, 80% credit. Anyway, that's a lot of stuff thrown at you again. Stay as caught up as you can on these. Do as much practice as you can along the way. Questions in the book, homework questions, extra questions tossed out in class, at problem sessions, anywhere we do these. Do as many as possible, because now is where practice really kicks in. So thank you for tuning in yet again. And I'm going to end this, and I will see you at the next podcast. Have a good day.